Okay, so in this video, what we're going to do is we're going to take a look at circular motion. But before we get started on there, I just want to recap a few things. So what I'd like to do is pause the video and have a go at answering these questions in your booklets. Okay, so now you've had a chance to have a crack at them. Let's see what we should have here. So the effects of a force can change an object's speed, it can change its direction, or it can change its size or shape. When we say size, what we mean is keeping it the same shape. So let's say it was a square, it just makes it into a bigger square. Shape would mean we're turning the square into a rectangle, something along those lines. What happens if a force acts parallel to an object's velocity? So let's just sketch a quick diagram to show what that means. So let's say we've got a box. It is traveling this way. So forces acting parallel to an object's velocity would either be that way, or it could also be that way. Either way direction, they're parallel to it. So in terms of what will happen, the direction does not change, but the speed does. So if we're looking at it, this force here would make your speed increase. This force here would actually make your speed decrease, for example. So what happens if force acts perpendicular to an object's velocity? So again, let's give ourselves a sketch so we can see what that looks like. So we've got the velocity again coming across this way. So that would mean the force was either acting that way or it's acting that way. That's what we're describing here. And the effect of that will be the direction changes, but the speed does not. So either it's going to sort of curve around like this, or it's going to curve around like this, depending on which way you apply the force, but the speed will stay the same, and that's going to be important later on, so bear that in mind. Finally, how is acceleration defined? Again, this is going to be important later on. It is defined as the rate of change of velocity, or the velocity change per second, if you prefer it that way. That's what we mean by acceleration, and the fact it's velocity in here is going to be important later on as well. So let's get into circular motion now. So first of all, what do we mean by circular motion? Well, first, the simple thing is it's an object traveling in a circular path, like you can see down here at the bottom. And the second key thing is it's doing it at constant speed. So what does that mean? It means it's traveling the same number of meters every second, wherever you may, so whether A, D, C, B, wherever you like, it's going the same number of meters per second, but that doesn't mean its velocity is the same, and that's going to be important. So its speed is the same, but its velocity isn't. And we'll talk about why that is later on. So if we actually describe the velocity of an object at different points, so the velocity is always tangential to the circular path. So that's the first thing. We'll see what that looks like in a second. The length of your velocity vector is the same at all points. Why? Because it's going at constant speed. But the direction of the velocity vector is constantly changing, and that's also important. So in terms of what that looks like, so when we say tangential, what we mean is in the directions you can see here with these red arrows. So just to add something on, so if we do, so this, if it's in this direction, it's described as radial. If it's like this, it is described as tangential. And that's because this line is effectively a tangent to the circle at that particular point there. So that's just some language that we use. So velocity is always tangential. So wherever we look at it in the circle, that velocity vector arrow will be drawn as a tangent. It should be the same length everywhere, which you can see on the diagram, but its direction is changing because you can see at A, it's to the left, D, it's down, C, it's to the right, and B, it's upwards. So we can see the velocity vector is changing direction. Okay. So question to ask ourselves is this object accelerating? And this is why it was important at the start that we defined acceleration accurately. So acceleration is the rate of change of velocity, and that's why it's the key we have velocity in there. So since the direction of velocity is constantly changing, and because velocity is a vector, this means velocity is constantly changing, even though its magnitude, or its number, if you like, is still the same. Because its direction is changing, it's a vector, velocity is constantly changing. This means that the object is described as accelerating. Because remember, acceleration is the rate of change of velocity, if velocity is changing, it must therefore be accelerating. And that's our logic there. So then if we accept that the object is accelerating because its velocity is changing, the next logical question to ask is, well, acceleration is a vector, and vectors have direction. Which direction is the acceleration? So another way of phrasing that question would be to work out what vector we need to add to VA, so the velocity at A, to produce VD. So let's draw that as a diagram. So to start off with, the velocity is going to the left, and we want to end up with velocity going downward. So we have to ask ourselves, what vector do we need to add to A to produce VD? And it will be this vector, because we've done the rules of vector addition before. We know we have to go on the end of VA, we had to add this mystery vector, and it needs to end up so that VD goes from start to finish, like this. And I'm going to call that delta V, or change in velocity, because that's what we need to essentially add on to VA to produce VD. Okay, so the thing to notice, if we actually put that onto our diagram, is essentially this delta V is acting towards the center of the circle, so it's sort of over here. So you can see here, we've got a change in velocity directed towards the center of the circle, sort of like our midpoint between A and D. So now let's have a look at another point to see if this rule still applies there. We'll go between C and B now. So we want to end up with VB, so we need to work out what do we need to add to VC to produce VD. Well, we need to add this vector. So the change in velocity is now like this one. So you can see that that is effectively here. So our change in velocity is directed in this direction here, again, towards the center of the circle. And this applies generally to circular motion. A good general idea to have is for an object to be in circular motion, the acceleration must always, or the change in velocity must always be directed towards the center of the circle. Okay, so using Newton's second law, that tells us something about the resultant force as well. It tells us it must also always be directed towards the center of the circle. So that should answer our kind of follow-up question. So if we've got acceleration, that requires a resultant force, and if the acceleration is towards the center of the circle, our resultant force must also be towards the center of the circle. Okay, so now we've established that there is a resultant force and it is acting towards the center of the circle. A question that we might ask ourselves is the resultant force doing any work? So if we're applying a force to an object and that object is moving or changing its position, we might expect there to be work done. And I think there's two ways of answering this question, and I'll show you both. So the first way of answering this question is to think about what work is. So work is when we change the energy of an object. And it's going at constant speed, so the kinetic energy isn't changing. So because energy is a scalar, direction doesn't matter. So kinetic energy is not changing, so the force must not be doing any work. Otherwise, the energy of the object would be changing. The other way of approaching this is thinking about how work done is calculated. So the resultant force is towards the center. So if we take one example here, so here the resultant force is that way. Here the resultant force is this way, or this way. The resultant force is always directed towards the center of the circle, or it is directed radially, we might describe it. But the object never actually moves closer or further from the center of the circle, as it stays at the same radius the whole time. So the distance moved in the direction of the force is 0. So if we plug d equals 0 into the equation, we can see no work has been done. So however way we think about it, this force that's acting is not doing any work. It's not changing the energy, or there's no displacement in the direction of the force. Either way, we end up with no work being done. Okay, so looking at something that's going beyond the specification, question you might ask, well, okay, so there's a force on the object. How big does that force need to be? And to come up with this, what we need to do is consider the velocity of an object separated a very small distance around the circumference. So what I'm going to do is I'm going to draw two triangles here. One is the velocity vector triangle, and one is a distance triangle, if you like. So on this left-hand triangle, I'm using the same logic I have been the whole time. I'm going, what do I need to add on to VA to produce VB? And we're calling it the change in velocity expression here. Okay, so that's one triangle in there. So if we actually dot this on, so this is kind of where we're working on here. We're going to say that these two are separated by an angle theta, and that theta is going to be the angle between VA and VB as well. So this is essentially what we've done, and we're saying that this angle is really, really small because we said it's been separated by a very small distance. Now what we're thinking about, so on our distance triangle, let's change color so we're not getting our things mixed up. What we're saying is across here, it's traveled a distance d. Now in reality, what it's actually done is it's traveled around the circumference. But if this angle is really small, this straight line distance and this arc distance are pretty much the same number. So we are making an approximation here. So that's what is shown on this one here. And we know these other two sides of the triangle are just the radius of the circle here. So on our distance triangle, these are all distances we've got on here. On our velocity triangle, these are all velocity vectors that we've got there. So those are our two triangles. Now these two triangles both have this same angle theta in them, which means they are similar triangles. So what we can do is we can say that delta V over V, so delta V is the length of this side, V is the length of one of the sides of this isosceles triangle, must be equal to D over R, because they're similar triangles. And what we can do is produce an expression for the change in velocity in terms of the distance, like the speed or the velocity. Well, actually, no, this V now stands for speed because it's the length of the side, so it's just the magnitude. So this is now essentially speed. And then we've got the radius of the circular path. Okay, so that's our starting point for getting to the force. So taking that forward, we know acceleration is the rate of change of speed. So what I'm going to do is I'm going to define both sides by the time to go from A to B, which I'm going to call t. So let's actually label that so we're clear. So this is the time. Okay, so that's our time to go from A to B. The other thing to spot in this is that this distance divided by time is average speed. And given that it's going at the same speed the whole time, we can just replace that with the v that we've been using for the speed of the object, and we get that this is equal to v squared over r. Now, that's going to mean that essentially the acceleration can be described as the speed squared over r. That will give us a value for it, and we know the direction is towards the center, so we can actually describe the acceleration vector. It's calculated by this, and it's towards the center. Now, we know that resultant force is equal to mass times acceleration. So that means if we multiply that expression by mass, that will be an expression for the resultant force. So if we want an object to go in a circular path, we need to apply a resultant force equal to mv squared over r directed towards the center of the circle. That's what this is telling us. Okay, so then essentially what we can do is ask ourselves is, well, what if the force isn't that value? Well, things can happen. So if the force is too big, the object will spiral in towards the center of the circle. If it's too small, it will spiral outwards, away from the center of the circle. So it kind of look like these two pictures here. So circular motion is a very precise condition to achieve. We have to apply exactly the right force if we want an object to go in a circle. So when we're building things like satellites and things like that, we have to be very careful with our calculations and get our satellite to go at exactly the right speed, at exactly the right distance, if we want it to keep going in a circle. Okay, so at the end got pretty complicated in there, so don't worry if you found that confusing and you're not following that too well. The key things I want you to focus on are, can you describe the three effects a force can have? Can you describe the effects of a force if it's parallel or perpendicular to velocity? Can you describe the direction of the resultant force or the acceleration for an object that's traveling in a circle? And can you explain why an object in circular motion is accelerating? And if you can do those four things, that's absolutely great. And if you can do some of the stuff I was doing at the end, that's even better. But that's what I want you to be clear that you can do.